Welcome to the second lecture on Foundations of Cognitive Robotics. In the last class, I talked about a basic introduction of cognitive robotics, where I told you that what is the source or inspiration of this term cognitive and how cognitive robotics is different, is unique from other branches of robotics. I also told you, if you remember, that what are the different types or characteristics of interactions that are possible in a robotic system in order to develop an intelligent robotic system. And we have made these graduations from strong to weak artificial intelligence, strong to weak AI. Like for a strong AI system, I told you that embodiment is not a precondition. You can have simple coupling, you can have historical coupling with the environment, and that will be good enough for a strong AI system. Whereas for a weak AI system, where we are talking about things like cognitive robotics, physical embodiment is very much required. Now there are two subcategories under physical embodiment, which are organismic embodiment and organoid embodiment, and I will talk about these different types of embodiments in this particular lecture. Also, I will tell you that how we can develop such cognitive robots using certain special class of materials called smart materials, and thus we will be able to build up organismic robots, and there will be a hope of developing cognitive robots through that. So in this second lecture on foundations of cognitive robotics, we will focus on organismoid embodiment. Okay, so all other couplings, structural couplings or historical embodiment, and the very futuristic embodiment, which is organismic embodiment, these are the things which we will not focus at this moment. Organismoid embodiment, which is the basic requirement for a cognitive robotics, will be in the focus first. Now, when we will talk about organismoid embodiment, what is it that comes into your mind first? Remember, in our last lecture, I have shown you a small video from Honda on the performance demonstration of a robot, which is a humanoid robot. That's the Asimo robot. Now this particular robot, how do you classify it? Would you classify it to be an organismoid robot? And if you classify this to be an organismoid, wouldn't it be a good idea to actually look into that how much humanoid organ-like, it is basically developed in the light of developing a human-like robot. So how much human-like is this particular robot? So let's look into Honda specifications and let's see that how much human-like is this Asimo robot. So we'll talk about the building blocks, and in this direction, let's look into what goes into the Asimo robot. Now Honda engineers have created Asimo with 34 degrees of freedom. This 34 degrees of freedom essentially means that there are 34 independent ways in which the Asimo robot can move its different limbs or body parts, and that actually helps it to work and perform many tasks much like a human, exactly not like a human, but much like a human. You have seen in the last class, in the last video, that I have shown that how it was delivering a glass of drinks to the lady. Now, this Asimo, apart from the fact that it is made of 34 degrees of freedom, structurally it is made of a lightweight material, which is a magnesium alloy structure, and it is combined with powerful computers. And it is these two combinations, that means by choice of a lightweight material and by choice of these 34 degrees of freedom, we are able to see the performances of the Asimo robot. Well, you may be interested to know that in comparison to the Asimo robot, what are the degrees of freedom to a real human? And then only we'll be able to understand, judge the performance of Asimo robot.
If we compare between the degrees of freedom in an Asimo robot, which is 34, and us in human beings, you will see that how astounding our creation is in comparison to one of the best robots that we have created so far. So if you look at the degrees of freedom that we have, first of all, we divide it into 5 major elements, that is the head part, the arms part, the hands part, the spine, and the legs. Now in the head part, you have the neck joint, which has 3 degrees of freedom, that is flexion, extension, lateral bending, and axial rotation. So that gives us the 3 degrees of freedom for the head. Next is the arms, and in the arms we have 3 different types of joints now. The shoulder joints, which has 2 movements, forward, backward, and up, down, and also the rotation, so total 3 degrees of freedom. And then the elbow joint, in which we will consider only 1 degree of freedom, although in some literature you will see that people add 1 additional degree of freedom, but because it is somewhat constrained, so we will keep only 1 degree of freedom for the elbow. And in the wrist joints, we have 3 degrees of freedom, that is up, down, left, right, and rotation. So in all, there are 7 degrees of freedom in each of the arms, and that means for the 2 arms we have 14 degrees of freedom. Now we come to the hands, the most dexterous part of our body. We have in 4 fingers 4 degrees of freedom each, that means 16 degrees of freedom to grasp an object. And then the thumb, it has 5 degrees of freedom. So combination of all of them makes it 21 degree of freedom. And for the 2 hands, that would mean 42 degrees of freedom. It's very, very clear that we are so far behind in terms of creating so many degrees of freedom in the hands of a robot today. Now we come to the spine. The lumbar spine combined has essentially 3 degrees of freedom, that is flexion and extension, lateral bending, and rotation. So that's the 3 degrees of freedom the spine is having. And finally the legs. If you consider the legs, it has 3 elements: the hip joint, which has 3 degrees of freedom, forward, backward, left, right, and rotation. The knee joints, which has essentially 1 degree of freedom, that is forward, backward. And the ankle joint, which has 2 degrees of freedom, forward, backward, left, right, rotation. So here we are getting 6 degrees of freedom, and for the 2 legs that would become 12 degrees of freedom. In all, we are having approximately 74 degrees of freedom in human beings.
There is also some more thing to compare. How about the weight of the Asimo robot with these 34 degrees of freedom, and how much of power it requires? Let's go back to the specifications of the Honda robot and let's check that. If you look at some interesting specifications of Asimo, which I gathered from the Honda's website, Its height is about 4 feet 3 inches. It's just like the height of a child. Weight is 50 kg. Well, that is little high in comparison to a child. Walking speed and running speed is slightly in the higher side, as we can see, 2.7 km per hour. Walking speed and running speed is about 7 km per hour. Grasping force little bit in the lower side, about 0.5 kg or 500 gram per hand. I am sure that a kid can lift slightly more weight than 500 gram. Actuator wise, this 34 degrees of freedom comes in the expense of 34 servo motors. In fact, that's what gives the maximum cost to this robot. And the control unit is having the working and operating control unit, wireless transmission units, etc. It has sensors, for example, in the foot. It has torso level sensors in terms of gyroscopes and acceleration sensors. And again, the negative side is the power. It needs a 51.8 volt lithium ion battery. It's very, very substantial. Also, lithium ion battery is quite dangerous under wet condition. And the operating time that we get, that is also very low. If you look at it, it's just 1 hour. So, and the operation system is workstation or a portable controller. So what we can figure out from this specification is that there are at least 3 points in which ASIMO is still far away from a good organismoid robot. One is in terms of course, the degrees of freedom. The ASIMO has 34 degrees of freedom, whereas in nature, the human that it mimics, that has 74 degrees of freedom. And it has a substantially high weight, is more than 50 kg in spite of using very advanced class of materials. Also, it needs a very high power, and it can work only up to an hour or so. So these are some of the limitations of the best currently available robot, which is close to an organismoid robot. So all these things, what does it point to? What does it lead to? It tells us that we need to improve in terms of the overall weight or the bulkiness of the robot, and also in terms of the overall power consumption of the robot. So what is the solution in front of us? If we look into the new developments of muscles in this new age, we will see that there is a new branch of robotics fast expanding, which is also known as soft robotics. Now, under soft robotics, the robotic arms are meant to stretch and squeeze at every point along their length, and their movement cannot be described with simple geometric relations because it is too complex. It's a large deformation motion, much unlike the way we are used to do it, let's say, for a rigid robot system with the help of kinematic chains. It's very difficult to describe this kind of a flexible robotic link with this type of robotic system. So here you can see a octobot or a octopus morphology, kind of thing which is mimicked in an octobot system. Now, one of the things, if we compare between the robots and the animals, we would see that robots' traditional designs of steels, etc., is far stronger than any naturally living material. Let's say the nearest will be the teeth or the nacre, and if you go for softer materials like say wood or ABS plastic, then possibly it will be closer to the cortical bones or a squid beak. If you make your robot even softer, like high density polyethylene or polytetrafluoroethylene or polyurethane, then you will come closer to cancellous bones, ligaments, tendons, etc. If you can make your robot further soft, like say silicon rubbers, then you will get some of the muscles like cardiac muscles, and even in a softer range, almost close to hydrogels, you will start to get the skeletal muscles. So thus this comparison is amply telling us that the direction to which we have to take our soft robotics. But is weight is the only concern? No, we have to also keep in our mind that we have a concern of the power, we have the concern of this so many number of servo motors which makes it very expensive to afford. Now you look at the different variations of soft robots, like this one is a caterpillar inspired locomotion, and then a multi-gate quadruped robot, again based on soft material. An active camouflage one, you can actually play with metamaterials and optically coupled properties to develop active camouflage. Working in hazardous environments type of robots, and then worm inspired locomotion in robots, and then particle jamming based actuation, rolling powered by a pneumatic battery, and hybrid hard and soft robot kind of combinations. And then we have this snake inspired locomotion, jumping powered by internal combustion. Then there is a manta ray inspired locomotion and an autonomous fish. All these are various types of soft robots that are coming up very fast, and with the intention that how we can reduce the weight of the robot. But also, as I told you, that functionally you need to improve, you need to replace these classical servo motors in order to make it more sustainable, feasible, low power consuming, etc. So we need to think of the development of muscle based flexible robots. The first stage towards that is the development of pneumatic artificial muscles, or PAMs, and these PAMs were the first step where the air pressure is used in terms of compressing and getting a muscle-like motion from the system. Now, however, the compression itself is quite heavyweight, so we need to change from a compressor-based system to, let's say, a solid-state kind of actuator system. And one of the very interesting candidates towards this is ionic polymer matrix composites, or IPMCs. These are a general class of electroactive polymers. Like here you can see a 4-finger electroactive polymeric gripper which can grip up to the extent of 10.5 gram of rock, and this is used by NASA in a EAP gripper for extra outside the Earth in one of the planetary missions to collect the debris. I can show you that how this EAP would work. You can see that such a large deformation you are getting from the electroactive polymers, and then how each one of the 4 fingers have to work together, the last deformation, and then they have to grab the object, which is quite, you can see that it has deformed a lot. So that is something without the use of any motor is really challenging, just by deforming it with the help of direct transformation of electrical energy to mechanical energy and then placing it at a different location. You can do much more complicated works with the help of this kind of IPMC rockers. Today we have even more interesting group of materials which can perform amazing feats, and they can be easily embedded and integrated in order to form actuators which would go very well with soft robotics and can really make our dream of developing cognitive robots. These are the groups of materials which are known as smart materials. Now, before we talk about such smart materials, we have to keep in our mind that the mechanisms also has to be made compliant. For example, here you can see that this is a gripper, and the gripper ends, you can see a large deformation you can make with the help of these closing down between the two. Now what here has been done using the fingers can be also done with the help of smart materials, and then you can actually get a very large deformation. So even though the smart materials can be used at the back end, in order to get a large amplified motion, you need to make such contraptions of compliant mechanisms for grippers. Now let's talk about the smart materials. In this group of materials, the features of such materials are that they are basically functional in nature, and the basic energy forms that gets interchanged in such materials are between thermal energy to mechanical energy, between electrical energy to mechanical energy, magnetic energy to mechanical energy, or sound energy to mechanical energy. As I told you earlier also, that energy can only be transformed. So in this case we have to manipulate between these transformations in order to get our intended type of actuations or type of sensing. Now this materials behavior, which is why they are so much important for soft robotics, is that they are analogous to biological materials. Like they have the nature of adaptivity, cellular function, self-sensing, actuation and control. And moreover, these sensors and actuators are highly embeddable. So as different energy forms are interchanged in a smart material, let's look into these different types of smart materials from an input-output classification point of view. There is a broad group of smart materials like piezoelectric. In this case, the input is electrical energy and the output is mechanical deformation, mechanical energy. And then we have magnetostrictive materials, where the input is for the group of ferromagnetic materials, the input is magnetic energy, and the output is once again mechanical energy in the form of mechanical stress and deformation. And then for shape memory alloys, it remembers its original shape after being deformed, and it can go back to the original shape. So this is by actually exploiting the change from thermal energy to mechanical energy. And we also have some special groups of rheological materials which are like electromagneto-rheological materials, where it's the viscosity that changes in the material. So thus there are these different types of materials, and if we look at these from an input-output point of view, the inputs can be categorized in terms of electric field, magnetic field, stress, heat or light for that matter. Even light can be used as input. And outputs can be in terms of charge, magnetization, strain, temperature and light. Now, if you look at these, let's say like in a matrix form, then the diagonal terms are something which are the material properties, which is very common in material. So they are not very smart properties. But it's the off diagonal terms, particularly this green row column and this gray row, which is of very useful nature to us. For example, electric field as an input, and as an output it is creating strain, is what is known as reverse piezoelectricity. That is what is used in piezoelectric materials, or even in the IPMC example that I have shown you a few minutes before. And this is one such kind of an off-diagonal property of a smart material. Similarly, if you can achieve the deformations using magnetic energy, then it's called Joule effect magnetostriction. So this is also another off-diagonal term. For heat, for the shape memory alloys, it's thermally induced phase transition. And for light, it is photostriction. Now this green column this is corresponding to the actuator development. Many of these materials can be also used as sensors. And here this gray row is very important. Like if you use, for example, stress as the input, mechanical stress, and by exploiting the direct piezoelectric effect, you can build up a sensor which will give you current or charge as an output. Similarly, using Villari effect in some materials, you can get magnetic field change, magnetization change as an output. Change of stress creating strain is a very normal thing of elastic modulus. There is no smartness in. But if I change the stress and if the temperature changes, there is a thermomechanical effect that is related to it. And similarly, if the electric property changes, there is a photoelastic effect which is also equally interesting in terms of developing sensors. Now, if you compare these materials in terms of actuators and compare them with the traditional actuators like motors, like pneumatic actuators or hydraulic actuators, we are interested to know that in which way smart materials are actually better, in which way these smart material based actuators will be outstanding in comparison to all the traditional actuators. If you look at the response times, you can see that all these greens are the traditional actuation system, which is in terms of seconds or milliseconds. And here for smart materials, you get it in terms of 0.1 milliseconds, so it is even 1/10 of a millisecond. And that shows that why they are very fast, so their response time is faster. That makes them closer to this kind of organismoid robots. And also another interesting property is their accuracy. If you look at their accuracy, they are far accurate than most of these actuators that we are talking about. At least 10 to 100 times more accurate these smart materials are. So in terms of the speed, in terms of the accuracy, they are, an order or several orders of magnitude better than the traditional actuators. Now, the flip side is that the displacement is lower or the force is also lower, but these two things you can actually compensate by using suitable mechanical amplifiers or by distributing the actuators, the smart material based actuators, in terms of just like our muscles, you can distribute it and you can extract more energy from the system. Now, if you look at the piezoelectric materials, because in this talk, today's lecture, I'll mostly focus on piezoelectric materials. As you can see here that if I apply force and if I deform the piezoelectric material, you are getting a voltage that is produced in the system. So this is what is the reverse piezoelectric, is the direct piezoelectric effects, where you are applying the force mechanically and you are getting the voltage out of it. If we look at these piezoelectric materials closely, we will first see that they are not that very new. It was developed around 1880. As you can see that Pierre and Jacques Curie has developed the first actually found out this piezoelectricity, which is basically electricity from pressure. And contemporary electricities were like electricity from static, electricity from friction, it was a contact electricity, or electricity by heating up crystals, which was pyroelectricity. So when they found out that even pressure in a crystal can generate electricity, this piezo means pressure, that's where this new group came into picture. And as a result of that, Pierre Curie and Paul-Jacques Curie, both of them got Nobel Prize in Physics in 1903 on the direct piezoelectric effect. The direct effect signifies if you apply pressure on the piezoelectric material, you are getting electricity out of it. Similarly, at a later stage, Gabriel Lippmann theoretically predicted that the reverse is also possible. If you apply electric field, you will get a mechanical deformation, for which he got his Nobel Prize in 1908. That's on the reverse piezoelectric effect. Now, why piezoelectric material is so exotic? What is there so special in a piezoelectric material that actually give it this property that as you apply the mechanical force, you are getting an electrical charge out of it? Well, one of the very important group of piezoelectric material are these perovskites, named after a Russian geologist, which was discovered roughly around 1950 or so. And these perovskites are generally a ternary structure. That means it is made of three components. Like in this example, barium, titanium and oxygen. So there are three components which forms this crystal, this piezoelectric crystal. Now, what is so special about these components is that if you look at the structure, the crystal structure of this material, you would see that bariums are at the vertices of this tetrahedral, this tetragonal structure, and you would see that the oxygens are at the face centers everywhere, and the titanium, which is the source of this kind of piezoelectricity, is deep inside the geometric center of this tetragon. Now, this titanium is very precariously positioned, because if I apply a little bit force on this crystal from any direction, the titanium will get displaced from its center, and the moment it will displaced, as the titanium has a high degree of electropositivity, it will generate actually a dipole moment in this crystal, and thus a little mechanical deformation, the crystal is charged. And if you imagine that in any bulk material there are hundreds or millions of crystals, each one of them will get charged because of this deformation. Although the dipoles could be random in nature and you need to electrode it to make it spatially moving towards a particular direction, but those are the things I'll talk about at a later stage. Now, this is about the barium titanate structure. Similar piezoelectric effect you will be able to see in lead zirconate titanate, PZT, in lithium niobium family, in lead niobium family, in yttrium manganese family, and in ammonium cadmium family. The thing that would differ may be the Curie temperature. The Curie temperature tells us that beyond what temperature the piezoelectricity would not be there. So the piezoelectricity would be absent in a system. So that's what is the Curie temperature, which you have to keep in our mind, that you will not see the muscle, the artificial muscle that we are trying to build in action if the temperature goes beyond a particular level. Now, what is the constitutive equation of such piezoelectric structure? As I told you that for the direct effect, where you are applying mechanical stress, that is there in this large X, that X is the stress. So you are applying stress in the crystal, means you are increasing X, and as you are increasing X, you will see that the charge is appearing in the system. Remember, if you apply or increase the electric field, then also there will be charge appearing, but that's something which is pretty common, isn't it, for a capacitor type of a things like a dielectric material. So that's not what the smartness is. The smartness is where you are applying the mechanical stress and getting a charge out of it. Only a very few group of materials will show this, and the degree up to which it will show is governed by the small d, which is electromechanical coupling coefficient. The higher the d, the more will be the electric charge that will be generating in the system. How can we use this, that you are applying stress and you are finding charge? Well, they have a great use in terms of development of sensors. So the direct effect is generally used for sensor development. Now for the converse effect, where you are applying the electric field now, not the mechanical field. Mechanical field creating small x, that is the mechanical strain, is quite natural for any material. But you are applying electric field and finding the mechanical strain, that's something new, isn't it? And that is what is the basic equation that we will be using for developing these artificial muscles, and by applying electric field, mechanical deformations, and that is what is the converse effect or the reverse effect, the electrical stimulus creating the strain. Once again here you can see the same electromechanical coupling coefficient. That means the more the materials D will be, the more I will be getting the strain out of the same electric field. So these are the two very basic equations which will continuously guide us in terms of the development of actuators and sensors by using these two effects. I will now show you some applications of piezoelectricity. The first application as actuator is actually pretty common in terms of every day. You might have seen it, you might not have noticed, that is in printers. Say for example, if you look at this, you will see that you are getting this axial deformation by using two materials, one smart, one non-smart, like these two things together. You can make a bending out of the system. And this bending, you can actually put it in terms of controlling the flow of inkjet printer. So each one of them is actually pushing a droplet of a pigment which makes the printer. So this is one application. Another application is in terms of amplification of piezoactuator. So if you look at the piezoactuator here, the central part is where the actuation is taking place, and this actuation in the central part is very small, but because we have used a special egg-like structure, a little bit of deformation here can create a large deformation along the semi-minor axis of the ellipse, which is what is these amplified piezoactuators do. And look at the very last one. This is where the piezoelectric material is actually in an offset with a composite. Here also, because of this offset, by actuating this, you can get a large deformation out of the system. All these three things you can use some way or the other in terms of developing the actuators. So in this talk, I have told you about one basic block of a smart material, which is the piezoelectric material, and how this piezoelectric material can be used in terms of developing an actuator. And this actuator in turn can be used to replace those servo motors that I have shown you in that azimuth, and to make a robot more organismoid or organic-like robot. There are many other smart materials, and in next few lectures I will quickly cover some very prominent smart materials too. Thank you.